Hello, today I would like to introduce our research on the multi-band dipole antennas by multimode excitation for the massive connections of IoT. We have three parts. For the first part, we have the application background. The research is for the next generation personal mobile intelligence centers. Then we will introduce two novel methods to design dipole antennas. First one is both odd and even modes excited and tuned for a single pair of dipole antenna. Then we will introduce the algorithm for the fewest arms of multiband linear dipole antenna. At present, we know smartphones are our mobile intelligence centers for the connecting of cellular networks and a large number of IoT devices. But in the future, it's possible we have more intelligence centers or even replace smartphone as new generation intelligence center, such as smart glasses. We know smart glasses are better in the visual interaction with us, such as AR, VR, and MR, especially for AR glasses. It's widely considered as the next generation intelligence center. We also have other devices such as the smartwatch and smart wristband. It's better in body monitoring, and also have other devices such as smart earphones and others. When we observe the antennas of these devices, we could see a big difference. For smartphone, the antenna is made by metal frames, and the metal frames actually are monopole EFA or loop antennas. This antenna is based on the large ground, means the main board of the smartphone. But for some new devices, because these new devices are small, and it's possible that the tiny devices lack a large ground, such as the glasses antenna. The antenna has to made on the glasses legs or the frames, and others such as smartwatch antennas on the wristband and other antennas on the earphones. However, for intelligence center, it has two equipped with the ability of massive connection of IoT and present cellular networks. So we need multi-band thin dipole antennas. Let's see present dipole antenna. Here is a simple thin dipole antenna with a source in the center of the strip. Here is a common dipole antenna. For this antenna, the source is located in the exactly center of the strip, and it could resonate at all the modes, half wavelengths, 1.5 wavelengths, and 2.5 wavelengths, and others. But they will resonate in even older modes. What's the reason of the phenomenon? Let's see the input impedance. For each mode, the reactance is zero. However, the resistance knows such condition. For the older modes, the resistance is very low and could be easily matched to 50 ohm pulse. But for the even mode, older modes, the resistance is very high and approaches infinity. So for the even older modes, it can't be matched. However, actually both odd and even modes rarely exist. We can see the characteristic angles and the eigencurrent distribution of the first several modes of this narrow PEC strip. In present literature, you could see when referred to multi-mode dipole antennas, if we place a source in the center, such as this literature, they could excite the older modes. And if we offset the source, then both the first and the second modes could be excited. But what we want to do is excite both odd and even modes. It means all the first several modes can be excited. Firstly, we developed smart glasses. The smart glasses antenna is made by dual port. We have the port 1 embedded in the middle of the smart glasses, and it's the same as common dipole antenna. Together, we use a port 2 together with a CCE, capacitive coupling element, located at an eigencurrent minimum of the even modes. Then both the odd modes and even modes could be excited, respectively, by the two ports. Then we consider whether we could combine these two ports into one port. We made a T-shaped structure in the middle of the dipole, and for the odd modes in the proposed structure, the T structure will not affect the dipole antenna. But for the even modes, we could see in the center of the main strip, it has a high input impedance. However, because the T-shape is not in resonance of the structure, so it has a relatively low input impedance, then the current could go into this T-shape, and then the bar on the T-shape will serve as a new CCE for the excitation of the even order modes. The simulated result can support our analysis. Here is the normalized current distribution for the first 7 modes of this structure. After the excitation of all the modes, another problem is how to tune this mode, and we have so many modes excited. We know that the desired frequency not definitely at the multiples of the fundamental frequency. So we have to develop the tuning method. Here we use two structures. By the combination of these two structures, we can tune any even single mode. Here is an indentation in the center of the dipole antenna. If the indentation structure is located at the eigencurrent maximum, then the electrical length will be bigger and the resonant frequency will be lower. However, if the same indentation is located at the eigencurrent none, then the electrical length and the resonant frequency will stay the same. And the protrusion structure is just the opposite. If the protrusion structure located at the eigencurrent maximum, it has no effect to the resonant frequency. However, if the protrusion located at the eigencurrent none, the electrical length will be longer and the resonant frequency will be lower. Here is the simulation result of a characteristic angle for verifying this analysis. Here, only the odd modes resonant frequency is changed. For this structure, only the even modes resonant frequency is changed. In our example, we arrange a pair of indentations at here, and then it could excite only this mode, 2-lambda mode, to the desired frequency. Here is a prototype. Another method is on the algorithm for the fewest arms of multiband linear dipole antenna. Here is the present multi-arm dipole antennas. They usually use one pair for one frequency. It's easy to simple and quick to design. Here is a figure to show the number of arm pairs versus the number of frequency bands for the multi-band linear dipole antenna. You can see most of the proposed antennas are on or above the 1-to-1 line. It means that we usually use one pair for one frequency or even more than one pair for one frequency. So here a problem is raised. What's the fewest number of arms for any multiband thin dipole antennas? Before discussing, let's see an index for indicating how strongly a mode is excited. It's a mode winning coefficient, MWC. Here, MWC is decided by the eigenvalue of the mode and eigencurrent of the mode, and here the impressed electric field is from the source. So if we want a high MWC, means this mode is successfully excited. It requires, firstly, a near zero eigenvalue. This means this mode is at resonance, and together we need a high MEC. It means it has a strong coupling for the excitation from the arranged source. Then we could conduct some simulations. This is a result from the simulation of FICO, and the x-axis is a fitting location, relative fitting locations for the first three modes of this simple strip, or say dipole antenna. The y-axis is the MWC, meaning the degree of excitation. You could see that for the fundamental mode, the half wavelength mode, red line, it actually could be excited in a wide range. Note a specific point is it could be in a wide range. And for the one wavelength mode, the green line, it could be excited in the left part or in the right part. And for the third order mode, 1.5 lambda mode, it could be excited in these three ranges. So from this figure, we can see the excitation of any mode can be in a range instead of a specific point. So here we could use the method of sharing arms for the design of multiband dipole antennas. For the algorithm, we use two indexes to evaluate the excitation of any mode. One is L over R. It shows the relative location of the port. And another index is L plus R. It shows the resonant frequency because L plus R is the total length of a pair of a dipole. Here is the flow diagram of the algorithm. The key concept is the algorithm is based on sharing arms. It needs to seek a set of lengths of U left arms and V right arms that could satisfy the requirement of all the T modules. T is the required frequencies. Then we can find the fewest arms of any multiband linear dipole antenna. Finally, let's have a conclusion. In this presentation, we introduced two novel methods on multiband thin dipole antennas for the next generation personal mobile intelligence centers. First method is exciting both odd and even modes for a dipole antenna. Here we use only single pair of arms. And this method needs an additional feeding structure. And then it could be tuned by indentations and protrusions. This method can be applied when not restricting the order of harmonics. For the second part, we introduce the method of sharing arms for the fewest number of arms. The algorithm of the fewest number of arms is concluded. In this method, the embedded port is in the middle of the dipole antenna as common dipole antenna. Then, the highest order of harmonics can be predefined before the algorithm. This algorithm could be applied when restricting highest order of harmonics. So that's all. Thank you.